Hi, I'm Howard.
I'm Samy.
I'm Stan.
Proximal operators are key building blocks in many first-order optimization algorithms. The proximal output solves a mini-optimization problem. And today we are interested in solving optimization problems where we want but do not have exact proximal formulas. Throughout, even if our function is smooth, we shall assume we only have access to samples of function values.
There are four main ingredients to compute proximals of general functions: Moreau envelopes, Hamilton-Jacobi PDEs, the Kohlhoff transform, and Monte Carlo sampling.
A Moreau envelope, shown in orange, is a smoothed out version of a function f, shown in white, with the same global minimizers. Formally, we define it using this minimization formula. What's important here is the proximal of f can be written in terms of the envelope's gradient, as shown.
Would you believe it? The envelope U is the solution to a Hamilton-Jacobi PDE. Ergo, we get a smooth estimate of U by solving with an adder Laplacian. This is beautiful. Holy mackerel.
Now, using an idea from Kohlhoff, we can use a change of variables from U delta to V delta, which takes this exponential relationship. This is nice because V delta solves a heat equation, which has an explicit formula. Using the heat kernel, we have an explicit formula for V delta. We can then rewrite the Moreau envelope, its gradient, and ultimately the proximal operator in terms of convolutions. Since the heat kernel has unit mass, it can be treated as a Gaussian probability density. In this case, we can approximate the convolutions by sampling.
Putting everything together, we see the proximal is approximated by this gradient formula, where we replace the envelope by the viscous PDE solution, which we prove is an accurate estimation. We can implement all of this via a relatively simple algorithm. Essentially, what we do is we get samples yi's from a normal distribution, we evaluate the function value at those points, and then we combine these estimates together using a softmax.
Now that we know how to implement H-J-Prox, we can use it to solve optimization problems, even when the objective function is unknown. In this example, we consider a problem where we only have access to a noisy oracle, subject to linear constraints. With H-J-Prox, we can use off-the-shelf methods such as the linearized method of multipliers to solve this problem. On the left figure, we fix a number of samples and test the performance for different values of delta. We observe that small to moderate amount of smoothing performs well, but when delta is 100, we oversmooth our approximation of the proximal and lose accuracy. On the right figure, we fix a smoothing value and test the performance when different number of samples are used to approximate H-J-Prox. As expected, we observe that more samples lead to more accurate solutions.
This work gives a simple H-J-Prox algorithm for estimating proximals. This estimate has desirable smoothing properties, and it can be embedded in optimization algorithms. Check out our paper for more details.